the 5-3 beta lesson. Right, and here's one of the edits that I made. So I went to the 5-3 lessons, and I took out that and symbol and replaced it with set notation. As I was looking through the College Board, the questions on AP Classroom, for your assessment next week, they use set notation, so I went back and edited this. So before, this looked like it said the probability of A and B, and it was then inverted B. So I changed the intersection symbol, because that's what you're going to see next week. So this is been on the Alphapedia. The probability of A intersect B is the product. The probability of A times the probability of B given that A happens. That doesn't change. The vertical line segment is read as given. And then it's algebra 1 to get what that means by itself. This divides both sides by the probability of A. Okay? When you look at this, right, you're sandwiching this. The B is sandwiched between the two A's. You can write it the other way. You can write it as the probability of B times the probability of A given B happened. But you can't turn it this way. It's not the probability of A times the probability of A given B happened. You have to sandwich either the B or the A in terms of the events. Okay? Tree diagrams. So we're not going to do any tree diagrams. If you find them helpful, they're essentially like Venn diagrams. They're something that you would do as a draft to help you prepare the two-way table. So if you find it helpful, yeah, then you draw the tree diagram and take your work to the two-way table. Like, you know, some people pick up two-way tables faster than other people do. Well, there's no, it's not a race to see who gets it first. The issue is, if you need, for your comfort level and your confidence, if you feel comfortable building Venn diagrams and tree diagrams before you load the two-way table, then do that. But the explanation is pretty thorough in the textbook about tree diagrams. We're just going to go right to the two-way table. Okay? So we're going to pause the video, and you're just going to two questions. Now, two questions are, one of them, all right, so let's look at 75. Here's your two-way table. Now, it doesn't matter whether you made the sevens the rows or the columns. If you have 7 as being rows and green and not green being columns, that's fine. So I'm here. The sum equals 7. All right. The sum of the dice. The sum of that column is 6, because there's 6 ways to roll the 2 dice and get a 7. You can get 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. There's 6 ways that it happens. There's 36 total outcomes, because there's 6 faces on the green die and 6 faces on the red die, and implies multiplication. If you look on page 214, you'll see that 314. So on 314, you have this 6 by 6 array. There's 36 cells in it. So the sum of not getting a 7 would happen 30 times. How about the green die equaling 4? Well, there's 6 ways that could happen, because the green die could come up 4 with any of the red die combinations. 4 of the 1, 4 of the 2, 4 of the 3, 4 of the 4, 4 of the 5, 4 of the 6. And there's 30 ways that the green die doesn't equal 4. And then we fill in these cells You'll have to balance that, you'll be there. We want to know if these events are independent. The green die is 4 and the sum is 7. That's this sum. Green die is 4 and the sum is 7. So we go to the sum of the row. 6 times 6 is 36. Divided by 36 is 1, which is confirming that they're independent events. And we drew that two-way table up there earlier in the week and left the one cell empty. You saw that events are independent if they're in proportion. 1 to 5, 5 to 25. So when you think about it in context of the question, is the sum being 7 independent? Even though that red die has to come up 3 for the sum to be 7, because the green die was a 4, those events are independent. It's not the definition of, it's not the language arts definition of dependent. Okay? So, that's all for 75, so you're going to go pick up with 81. Okay, back to 81. It would look like this. For 81, they tell you, ready? The sums of the columns. Now, if you wrote them as rows, they're telling you the 88% of the customers buy regular gas. The 2% buy mid-grade, 10% buy premium. That's given. So you put that at the sum of your column, or if you wrote them as rows, that's where you put the sum. Then what? Then they turn around and say, of those who bought regular, 28% pay with a credit card. So our rows are cash and credit. When you go to regular, it's 28% of the regular gas buyers. So it's 28% of the 88%. That's how I'm filling out the rest of this row. Then this value has to add up to 24.64%, give you 88%, or you just multiply 72% times 88%, which is what you're doing if you build a tree diagram. At the end of these branches here, you're getting those products. So the issue is, ready? You want to build the entire two-way table. Then go back and worry about the question. You don't want to stop when you have the answer to A. And this happened on the AP test in May, where you had multiple questions based on the data. So you're way better off building the entire two-way table and then going back and harvesting your answer. So A asks, what's the probability use a credit card? Well, the credit card would be, success would be a credit card, which is the sum of this row over the total of 1. And that would be a little less than 30%. You're only getting this answer after you do these 3 products and add them up. What's the probability you picked premium gas given you pay with a credit card? So premium gas, ready? Given that you pay with a credit card. So here's premium, there's the credit card. You've got this cell, conditional probability, it's not over 1, it's over the sum of the credit card row. It's a little over 14%. Okay? So if you find it helpful to build a tree diagram before loading the data in the two-way table, I would encourage you to do that. But you don't have to. You can just go right to the two-way table if that makes sense to you. Okay? So for the children that are at home, that's all for the beta lesson.